Peter, when it comes to power electronics, you said to me earlier, it's about moving the energy around. What do you mean by that?
Yeah, actually we are moving the energy locally from the point of generation to the point of consumption. But in between, we also need to change the, let's say, configuration of the energy from high voltage to low voltage, etc. So this is what we mean with moving around electrical energy to the point where we need it and to the, let's say, configuration we need.
And that includes everything from the massive power generation plants to solar to all the way down to uses in home, industry, cities.
Absolutely. That's a modern trend of electricity generation. It's driven by power semiconductors, especially the renewables. The transmission itself is more and more power electronics, power semiconductor driven. And at the consumption side, historically, we had already a lot of power electronics. But since we have so many new applications, including e-mobility, including storage applications, so there's more and more power semiconductors being involved in the game.
So where does silicon carbide technology fit into this?
Yeah, silicon carbide is everywhere where you need highest efficiency. So of course nobody wants to lose the precious energy generated maybe in a solar panel or by a windmill during transmission or even between the final conversion steps. And silicon carbide enables really leapfrogs in efficiency of the power conversion. In many applications we can drop the losses during the conversion by 50% and more. That's an amazing contribution of SiC to a greener world.
Now, and as I understand it, not only is it more efficient, it's smaller, so you have less materials, the design and how you create the things is different, so there's a huge sustainability angle there as well.
Correct. So of course we can save space by various benefits enabled by silicon carbide. One is a higher efficiency, what effectively means you need less efforts for cooling, smaller heat sinks, maybe no water cooling, no forced cooling in power electronic systems. So the whole this peripheral materials and efforts are significantly smaller when going for silicon carbide in a conversion system. And the second benefit is silicon carbide enables much faster switching processes in the energy conversion process, and this typically also leads to the reduction of passive components in size and weight, namely inductances. And this effect in the end gives us a material saving and also weight and volume saving aspect.
I'm an electronic engineer way back in the day. I've been familiar with silicon carbide, it's been around 30 years. But in the last couple of years, you've got bigger wafers, you're using different technologies, you have the cold split. What's going on there?
Yeah, we had tremendous progress on the technology side for silicon carbide. You mentioned wafer diameters, that the introduction of 150 millimeter and now 200 millimeter makes the technology compatible with existing high volume and highly efficient fabs. We had tremendous cost down on the material and processing side that makes components more affordable. So more applications can create not just a technical but also a cost performance wise an advantage. Yeah, and also not to forget, we have at the same time a growing scope of applications, and especially the new applications are all requiring this high efficiency and compact solutions enabled by higher switching. So different factors were responsible for the big boom in silicon carbide. On the one hand side, the technology itself, but also the market, which was requiring the silicon carbide, and what is not to be neglected, the experience of the design engineers to work with silicon carbide.
True.
Also increased a lot over the last year. So there's not such a hesitation like in the infant times of SiC, where people had a little bit concerns to work with new components and faster switching. Everything was new, but this has changed, and now it's reality.
What does the future look like?
Bright, I would say. Exactly what you have mentioned. So we are now able to enter applications which were driven by completely different solutions, more mechanically driven solutions. Now semiconductors step in, which manage the power part, but the amazing thing is you can easily combine them also with intelligence. That's another big factor which, for instance, with the solid-state circuit breaker comes into the play, and also the solid-state transformer. It's not a dumb mechanical system which is just doing something. Now you can manage energy flows in various directions. You can create intelligent breakers which do not break down. They protect, but they come back alive. So again, it's a waste reduction because you don't have to throw away things. So a lot of very interesting opportunities we have ahead of us.
But just seeing the pace of change, what you guys are up to, and as we have more electrification, more renewable energy, more sustainability, efficiency, less materials, it's like, hey, good stuff. I wish you well.
Thank you very much.
Thank you.
Thank you.